Okay, so let's kick things off. We're now 5 minutes past the hour. My name is Nicholas Lane. Welcome to Flower Monthly. This is the Flower Monthly for March, and it's a very special Flower Monthly because it is the Flower Monthly that's right adjacent to the Flower AI Summit next week. Let me show you what we have for you this week. The agenda will be a few updates from the Flower generally, but then we're primarily going to focus on two really fantastic, interesting talks here. The first one is going to be given by Matt. Matt is at the University of Chicago, and he's been examining how you can pre-train federated models in quite a unique and interesting way. So he's going to explain to us all what tournament-based pre-training is all about. So I'm super excited to look forward to that. And then we have a chance to ask Matt a few questions and so on. But the following second invited talk will be by Dmitry Kolobkov. He did this work at GENXT, and it is going to be work that examines a really important application area of federated learning, one that's examining how we can use federated learning to advance the area of genomics. So I haven't seen a lot of work in that space. So I'm really interested to see what he's been able to accomplish here. Both of these talks used Flower to enable their research and examination. So it's really excited to see what people are doing with the software all the time. Um, Before we get to those talks, let me tell you about what is maybe the big thing for Flower this month. Not surprisingly, the big thing is the Flower AI Summit. We are going to kick things off for the summit next Thursday. That is March the 14th. And as it's a 2-day event, it's going to bleed over into March the 15th. The physical location of the summit is going to be London, but we have doubled down our efforts to make this hybrid experience really engaging. And so if you can't make it to London, I highly recommend to join online, and you'll get a lot of the experience, if not more, because you'll be able to interact with the other folks more easily, who happen to be also online as well. The summit this year has really exploded. We moved it to London because we had a lot of people asking us to attend and how we could make attendance more accessible. So we moved to the nearest most major city, and London luckily is a hotbed for AI, so it made a perfect fit. And just this afternoon, I really had to call it quits on the poster and demos because we had a rush of people trying to get in, and we're doing our best to accommodate them. I guess they kind of left it a bit late to submit their poster and demos, and we're able to accommodate many of them. But at this point, we really can't take any more. So I'm afraid that even though the link might still be available on the web as of right now, I think we can't take any more posters and demos. But I would highly recommend those who haven't registered yet to please do so, because we do have a limited physical capacity in the venue. And so if you want to attend in person, please register, I would say immediately. And similarly, if you want to attend online, register now as well, so you can get the updates that we'll provide to you leading up to the event. Just for a frame of reference, for those in London, both the after hours and the main event of the summit are about 5 minutes walk from King's Cross. Let me tell you a bit about what you'll see at the summit. It's a 2-day affair. First day, which kicks off at 1 p.m., is the time of the first technical presentation, and that will be on the Thursday and focused on AI research. So we'll be looking at a wide variety of breakthroughs, methods, applications, all related to how we can advance the state of the art of federated learning forward, and where the tool of choice here is Flower. We are lucky to have a healthy mixture of both talks given by members of Flower Labs, as well as people in the wider ML community who have been examining federated topics speaking. So we have a few professors, as you see here, talking about some of the research they've been doing. Most of them have been using Flower to do things ranging from developing a federated model for degenerative eye diseases to enabling smart campuses in a privacy-preserving way, towards doing heavy lifting of deep technical work that's appeared in venues like ICML and NeurIPS, dealing with things like personalization and concept drift. And so you'll hear about a lot of big, important topics and open problems in the era of federated learning on this day, as well as a roadmap of where Flower is going from many of us in Flower Labs. And there's in total going to be 17 of these invited external talks and a variety of internal talks spread across the 2 days, as I've sort of discussed. Also, within both of these days, are going to be a number of poster and demo presentations. And so I wasn't able to capture actually every single person who's showing a demo or a poster because I couldn't get the graphic generated soon enough. But so this is primarily a majority of the people who will be there. One of those faces you'll see there is Dmitry. He's speaking on Flower Monthly today. But there's a large number of researchers, academics, people working in AI labs, who have come, who are going to come from places like China, Korea, the US, the Middle East, to present posters and demos. And that was mainly because we just couldn't have enough sort of audience time to fit them all in. We want to also facilitate deep dive conversations. And these posters and demos will be throughout the 2 days. On day one will end around at 6 o'clock. And then for those who are physically present, we're going to go across the road to a wonderful social venue where we have a private area just for people attending the Flower Summit. It's called the Big Chill, right across the street. And from 6 o'clock till late, you'll be able to socialize and sort of unpack all of the information that we heard in that sort of afternoon session on day one. These are photos that I took myself when I went down there a few weeks ago. It had just rained, so it looks a little damp, but I'm promising you next week in London, it's going to be hot and a wonderful place to be. There's outdoor aspects to this venue, there's indoor, so we're ready for everything. And so that'll be a great thing to conclude day one. And then we'll come back the next day on March the 15th at 1 o'clock, and we'll do a similar deep dive onto a variety of presentations that focus on deployments, getting federated and privacy preserving and all those other related types of technology out there into the real world. We'll be hearing from folks who are building real systems, primarily with Flower, to make these things happen, learn from their experiences, understand how they've sort of met those sort of final challenges to realizing the application. And so again, we have a mixture of internal talks from Flower Labs people, and then other folks out there in other organizations, such as Samsung, the US Air Force, Amazon. We also have a special session with 3 lawyers who have examined what does FL mean under these sort of emerging AI regulations. And so we're going to have presentations and a brief discussion about this. And so we could start to contrast how conventional and federated forms of machine learning will play out as regulations evolve. There's other talks here that I couldn't fit it all on one slide. We've got people from Zama, folks from Zenzac, which is a subsidiary of Volvo. We have also not just companies, but organizations who are trying to nurture PETS technology, such as the UK has the Open Data Institute, who is trying to provide guidance about how you roll out, in particular, PETS technology. And so you'll hear all of this sort of deployment and real world knowledge on day 2, along with an additional set of posters. Many people are presenting posters on both days, and so you get a chance to talk to them multiple times. So that is a quick summary of what you're going to see at the Flower AI Summit. It is going to be the world's largest gathering of federated learning I'm aware of, and that has ever happened up until this point. Fully virtual if you can't be there in person, but if you can make it, I highly recommend it. And please register now so we can make sure you get a seat if you're going to be there in person. So that's what's happening for Flower this month. I'm now going to hand over to our two wonderful speakers. The first speaker is Matt Baughman. He is a PhD student in the University of Chicago, and he's been looking at this topic of tournament-based pre-training that I think can have large implications for how we do federated learning in many specific types of contexts. So I'm going to stop sharing, hand over to Matt, and then we can see what you all think and ask him a few questions. Over to you, Matt.
Cool. Thank you, Nick. Let me quickly share my screen. Hopefully it's still working from when we tested 2 minutes ago. You see it all right?
Yeah, it looks great.
Cool. So yeah, like Nick said, I'm going to talk to you a little bit about this method that I think saying that we developed it is a little bit of a stretch, but we kind of repurposed this for use in federated learning, and especially federated learning in austere environments. I'll talk a little bit about the collaboration that kind of gave rise to all the different needs that went into us deploying this, and kind of the current tests that we're doing, what our interests in federated learning are. Because I have a secret to tell you. I am not a machine learning person. I'm not a federated learning person. I am by trade a systems person. So I'm part of this group called Globus Labs. Some of you may have heard of Globus. It's a company, startup, nonprofit, kind of whatever you want to call it, that was spun out of the University of Chicago back in the late 90s, I believe, 98 or 99. That focuses on very, very, very large scale data management. So we're doing large management across different institutions, companies on the scale of petabytes per client. And we're closely integrated with Argonne National Laboratory, so working with the large scale systems there. This group was kind of born out of this collaboration called the Computation Institute, which has now been adjourned, I guess you could say. But the whole idea was we wanted to operationalize these computational resources for real science. A lot of academia in general, but especially computer science applications focus purely on kind of, can we do this? Do we get good experimental results? But one thing that we love about Flower, and it's a vision that we share, is really operationalizing these methods for real scientists, real people out in the field. So that said, my main focus is on kind of cost-aware computing and creating these dynamic systems that allow folks, specifically domain scientists, to use large-scale supercomputers, as well as including devices that range from these supercomputers all the way down to very, very small edge devices. My belief is that people should spend time on their own science and not have to spend time on doing the system stuff. That's what I'm here for. So we have several kind of ongoing missions with regard to this. One of our big projects was previously called FuncX, now called Globus Compute. It's a serverless framework that effectively allows folks to push compute and push data wherever they want. We call it a fluid execution framework. It's also designed to be extremely lightweight, but also extremely scalable. So we have great scaling tests going all the way down to kind of these single core smart devices that are running off of tiny battery packs and solar panels living out in the forest somewhere, all the way up to scaling to thousands. I think maybe we've even reached tens of thousands of nodes on the largest supercomputers, top 10 system kind of class. This has since, you'll see the architecture diagram shows that it's still called FuncX. This is because it's a little bit older. It has since been rolled into a semi-commercial product with Globus called Globus Compute. But it's the client side is still open source. So anybody here who wants to go try it out is more than welcome to go try it and use it for their own research and purposes. but the kind of vision that we see stemming out of this type of technology is a national, what we call a continuum, a computing continuum of facilities and compute resources for science. So there's this great system in the US called ESNet, the Energy Sciences Network, that connects, I believe it's 29 science user facilities across the United States with high priority, high bandwidth interconnects. And these include many supercomputers, including currently the top 2 systems in the world, soon to be the top 4, hopefully, as well as many actual experimental science user facilities. So in this graphic here, we have the major accelerator laboratories across the United States, because the data collected from these, I think, totals somewhere close to a petabyte a second. Obviously, you can't store that, but you have to process it in time and then distribute the relevant information across the entire ecosystem. Obviously, if you started a streaming transfer of anywhere close to a petabyte a second, even a terabyte a second between these different locations, people would probably get upset. And so we're thinking about how we can create systems to automate what's important, pre-process what we can, and move what we absolutely have to. Because of this kind of multi-site component, and especially the aspect of having to distill this data before we transfer it, a lot of folks are really interested in federated learning because they can effectively distill the data or compress the data by training a model on it at their local sites, and then just move those, quote unquote, just move those models around. Still very large models in many cases. But this also enables faster sharing of information. Some of the labs have semi-strict controls on what can and cannot be transferred or made publicly available. But this is effectively a manner of privacy preservation for some folks, data management for others, and really operationalizing that data that's, say, collected at the Argonne accelerator. We can send Berkeley a model that they might be able to use to drive experiments at their synchrotron facility. So kind of the collaboration that's currently going, I talked a little bit about the Computation Institute and how I got here as a systems person. But now we do have this project called Rural AI, which is a large collaboration. I think we're up to 7 or 8 institutions now. It might even be 9. Of folks that are really interested in bringing these AI tasks to small and large devices alike, but enabling AI in areas that historically don't really have AI-enabled technologies. We chose the name Rural AI because a lot of our applications are very agricultural, especially in developing countries or in areas of countries that don't have substantial access to heavy compute infrastructure. We've done a lot of work with native peoples in several different countries, looking at how we can potentially accelerate agricultural investment, agricultural knowledge by providing these types of services, and kind of decrease this idea of the digital divide between the compute haves and the compute have-nots. Many of these restrictions, poor network, stranded compute, very stranded data, are obviously problems that people are continuously solving. How can we do the most with what we have? But we really found that federated learning is a massive way that we can leverage the data and the compute that is available to not really waste, because that's the big thing here is we're trying to prevent computational waste, which is for all of us spending time on ChatGPT, which guilty. But we're burning cycles. As a systems person, that's a mandatory hobby. You have to be willing to burn cycles. But we want to make sure that for people in areas where these computational cycles, energy, network are valuable and precious resources, that we can use these resources as well as possible. This little robot here we have at the bottom is a great example. It goes through and it can measure all types of characteristics about soil quality and takes pictures of plants and weeds and pests and things like that. The problem is it produces about 3 gigabytes per second of data, which even with a semi-fast wired connection is a tenuous amount of data to continuously stream. And so this is kind of our main use case, is how can we process that data, selectively choose what data we want to learn on, and use the onboard resources in order to train small models that we can then hopefully use to regenerate data and produce even larger models in concert with dozens of others of these devices. Because this data is very noisy and it's very large and we can't offload it, we wanted to find a use case that could somewhat simulate the conditions that we see. So one of these data sets is the Wellington camera trap data set from New Zealand. It is a very unique data set because there are lots of well-labeled images and it's wonderful, except the subjects of each of the images are relatively obscure. This is one of the more obvious images. You might be able to see the bird, which now I put a bounding box around. This is definitely in the top 10% of visibility. And so it's highly non-IID data, highly sparsely featured data. And you also have the problem that it's a massive noise to signal ratio, because the images are roughly the same each time, except for perhaps a bug or a bird that's flying past the camera. Birds love this, animals love this because they have natural camouflage. But it makes it difficult for us to do interesting things with it, especially with the very constrained resources present on these devices. You can't run even the largest of the kind of state-of-the-art object detection localization networks like a YOLO won't even have a fighting chance on smaller resources like these. So we have to find kind of low barrier to entry ways in order to handle this. Additionally, remember, not a machine learning person, and so we want to find ways that are accessible to domain scientists that not only they can understand, but that are plug and play and don't require gross amounts of configuration or domain knowledge. And so the problem that we're kind of running into that we're trying to solve with these simple methods is the fact that with this high noise signal ratio, a lot of these features get washed away over time. We actually find, which is hysterical, and there are definitely ways around this, the individual models do relatively well, but they are definitively overfit. We've tried the standard repertoire. I should say our machine learning people, the proper machine learning people, have tried ways of ensuring that these models don't overfit. Then we end up really not learning too much about the individual animals, especially since some of the classes that we have double-digit examples, where others, like birds, we have over 100,000 images of birds. So not to mention that we have, again, these compute constraints. And in order to kind of prevent this washing away of learned features, so you kind of have to learn features to a level that they will survive this averaging, this aggregation across all of the different endpoints, but at the same time not overfitting. So we thought that, if there's some way to align these features prior to doing aggregation, prior to doing kind of more what we would consider proper federated learning, training and aggregation, this might give, in the process of gradient descent, kind of a good starting point, something that will say, hey, we have these features that we think are possible. Now, how can we double down on them? And so if we can align these features prior to training in a given training round, we thought this is a pretty good bet of being able to at least prevent some of this washing away when we're aggregating over hundreds of endpoints. There are definitively methods that are much more technologically savvy, also much more compute intensive, that involve a lot of math to compute similarity vectors across different features, order features by order individual kernels by the features that they've learned, do aggregation in kind of a piecewise fashion. But like I said, not only does this take more computational resources, it requires generally a level of understanding that many domain scientists might not have, and we don't want to assume that, especially since federated learning in its core is a relatively simple process, but the learning curve becomes very steep very quickly. We want to make sure that that kind of 0 to 1 is simple for scientists, where they might be able to say, hey, would my data set work? And not immediately get bad results and say, oh, federated learning, it's terrible. We never want to use it again. And so we came across this paper at SC a couple of years ago called Livermore Tournament Fast Batch, where basically they were training individual models on their individual systems at Lawrence Livermore Lab and taking the most performant network, most accurate network at each round, and then just distributing that as a global model versus doing some fancy aggregation. Wait, I'll just put this whole thing up. And so we thought, well, what if we do this and then distribute whatever that quote unquote best performing model is as the global model. And this way we kind of start with a semi pre-trained network that has that provides a grounding point of these aligned features for all models to start with, rather than just doing kind of standard random initialization. Again, there are much smarter, much more involved processes to do this. Definitely not claiming that this is state of the art by any means. This is the kind of 0 to 1 point for aligning features. And so by doing this process, we can begin to learn features and distribute those features globally versus doing this aggregation that will wash away the less strong features, especially for categories like the individual animals that we have maybe 10 images of. So the results, in some cases, they're very, very good. In some cases, they are not so good. What we really see here is that for a smaller number of endpoints, this does allow us to get over that issue of averaging away features. The problem is once we start doing this with too many endpoints, a lot of the distribution, the non-IID-ness, really just relies on kind of the luck of the draw. And so we don't get universally good results much above kind of the 60 to 80 endpoint range, just because no single endpoint has enough data to actually make a meaningful impact. And in some ways, it can ground the entire training process such that you might not be able to recover because you kind of get stuck in these local minima, and you can't really recover without injecting some sort of noise, randomness, etc. We do see additionally, if we go back, if I run back to this graph, a lot of these training rounds just sort of ended on the same value. It was very uninspiring. The funny thing is we tried a very wide hyperparameter sweep. Again, systems people, so we like the brute force approach. And we always arrived at kind of the same answer. So we believe it's just a characteristic of the data, because the largest class composes about 12%. And so it's really just learning the largest class and parroting that every time. But in this case, we see substantially more variability round over round, even beyond the pre-training round. And we think that's because grounding on solid features, then each model can kind of deviate from the pre-trained features as its data might require. But eventually the vast majority are going to kind of average back to this set of pre-aligned features. One thing that we're thinking about with this is potentially we could interleave tournament-based pre-training with traditional FL, and take that approach. That might have good results, but we aren't sure at this point. Right now we're working on validating this across wider data sets. greater set of architectures and different resource and endpoint configurations. So conclusions, future work, like I said, we really just want to generalize this. We want to see in quote unquote more real science use cases if this is beneficial, or maybe we just found the one application where it does so poorly that any type of perturbation to learning features might kick us into a beneficial training regime, but it doesn't apply anywhere else. So we are currently running tests. We're actually hoping to have them for this meeting so we could show off, haha, this applies to all these different training scenarios, but unfortunately, because the supercomputing conference deadline is coming up, all of the machines are largely reserved for people who aren't just running spin loops. Or I should say, are reserved for the people just running spin loops. So where does Flower fit in? This specific work, because we're just effectively playing around, did not use Flower initially, but we are currently working to integrate this with Flower, because like we said, Flower's vision really parallels our own, especially the use of real devices, and also being able to do simulation we think is huge. And so we want to integrate this method along with our other kind of FL-related workflows with Flower, both in simulation on the large machines, but also our real-world test bed. We're working on scaling Flower just to see kind of, how far can we push it before it breaks? So far, the answer has been we can push it really far, which is awesome. And we're thinking to definitely pie in the sky idea, and I'm sure that the Flower people will tell us that we're crazy and we shouldn't do this. But we're looking at the potential of integrating our Globus Compute serverless framework as the sort of communication backend for Flower. So using all of the Flower strategy specifications, input-output specs, but using this kind of serverless backhaul to be able to access these more remote devices that you definitely have to use sort of a fire and forget model, and kind of managing the communication ourselves. We have some students working on this, and we'll hopefully see good results, but like I said, we're not entirely sure. So at this point, I'll take questions. My email's at the bottom if you want to ask any additional questions offline, and then I also have a QR code to my Google Scholar there in case you're interested in my systems work versus my pretending to be a machine learning federated learning person. Thank you, guys.
Thank you. Thanks for the talk. Very interesting concepts. Anyone, if they want to ask questions, you could raise your hand. I could unmute you. We've got the Slack and other types of inputs. So anyone want to kick things off with a question?
Yeah, first of all, thanks for the great talk. And I just want to comment about the last thing and say not crazy at all. I think this is a very viable path forward to integrating Flow with other kinds of infrastructure that is already in place. And I think Flower Summit at Flower AI Summit next week will have some very good news for you, because what you're planning to do will become quite a bit easier.
Awesome. No, I'm definitely looking forward. Unfortunately, I can't come in person, but we'll definitely attend virtually.
We're also very pro systems people, so no need to have a big divide here. We're a big tent. Love system people, love machine learning people. I think I saw Javier had a question. Let me just allow him to talk. I'll click this button. Javier, I think you can speak.
Yeah, can you hear me?
Yes.
Yes. Okay. Yeah, I think this was super interesting talk. I have one question, a bit more machine learning, but I think it's very high level. So I think one of the problems when doing federated learning is, especially in the wild, like the example you were showing with these cameras in New Zealand, is that you don't have labels. So was your training doing some kind of unsupervised training, or do you think that's the way to go for this kind of super large scale federated learning systems?
Yeah, so in this case of this data, so I'll give you kind of two answers. In this data set, one of the reasons we use it is because it's almost 300,000 images, and they did have Each one was hand labeled, which is incredible. Big citizen science effort. So that was kind of the main reason behind using that. Regarding unsupervised learning, though, this is a huge push, especially with the applications that we've started looking at, and the folks that we've started talking to in kind of these domain science areas, especially experiment steering, having kind of a semi-supervised learning approach, where we can see like it's very easy to tell if a experiment ended poorly or successfully.
Mhm.
And then we can kind of backtrack and do almost a reinforcement learning thing with federated learning, potentially, across multiple sites, just to, like I said, with the synchrotron experiments, doing this kind of experiment steering where every part of the experiment relies on accurately and predictably rotating these samples so you can get the proper imagery from the synchrotron radiation. It's definitely not a solved problem. People have ways of doing it. But these are cases where you can't kind of go through and say, was this a good rotation? Was it a bad rotation? So there are definitely applications for unsupervised learning, especially like you said too, in these austere environments where we have to delete 99% of the images and can only transfer one out of every I think it's about 200 to 300 images. So being able to do accurate unsupervised learning, automated clustering is definitely something we're looking into and something that's going to be very important.
Yeah, I think it's super cool. Thanks.
Thanks.
Yeah, very cool. I think there is a baseline in Flower for doing single image unsupervised learning. So basically SSL combined with FL, if you want to check it out sometime. Or we can point you to that. Let's see, there's a question here. The question is, are endpoints analogous to clients in FL?
Yes and no. So our endpoints in Globus Compute is really you can think of it as the client very generally, where that is the kind of point of contact with the central, for us, manager, forwarder, for you guys, aggregator, server. However, in the Globus Compute case, each endpoint can have many, many workers, which you can think of as many, many clients potentially, each running its own machine learning task, especially in the large systems. These individual workers generally end up being single nodes, and your workflow is going to have some sort of inherent idea of parallelism that it can abstract on its own. But we also definitely recognize people who use individual workers on individual cores to do parallelism in that way. So yeah, long answer to your short question, you can have clients on the node level, the endpoint level, or the system level, really. Like if you were using a 10,000 node machine, you wouldn't want 10,000 endpoints. You'd want one endpoint and then some way to plug into the scheduler to control the rest of the resources.
I see. Okay. Yeah, that was an anonymous question from the audience. I think we're a little bit low on question time. Yeah, I think we'll end it there. But that was a great talk. Had some good questions there, and fascinating work. I like the fact that you've acknowledged that, federated as a method for training models is much more than just focusing on privacy, but it is an answer to many of these kind of underlying system issues where you might have you have a compute plane, you have a data plane, and you want to get a model trained in the best way possible. And this recipe is really powerful for certain situations. So cool, very good.
Yeah, thank you guys so much for having me. Really appreciate it.
Yeah, thank you. Let me just share my screen again. Allow me to introduce our second speaker. And so we have Dmitry Kolobkov. He did this work at GENXT, and it is examining federated learning within this application domain of genomics. And so I think this is a powerful, relatively untapped application area. I was super stoked to see someone working and diving into this area because I think Federated has a lot of potential for transforming the way that these models are built. And these models are right now being designed, and people are trying to figure out how they can integrate them into the kind of the existing network of data and companies and organizations out there. And so I think Federated is poised to really make an impact here. So with that, I hand over to Dmitry. If you, for those on the call, feel free next week, you're going to better meet Dmitry in person if you're at the Flower AI Summit. So over to Dmitry. Thank you for being here.
Yeah, thank you for inviting me here. And I would like to share the work of my team in federated learning on genomic data. So as Nick said, this is the area that would benefit immensely from federated learning, and yet the applicability of FL has been essentially not investigated. And we just recently published a study that that essentially explores the efficacy, the applicability of federated learning on genomic data. So I will provide the link at the end of the talk. So yeah, and of course it goes without saying that all federated models were trained with flower. So let's start. So every phenotype we develop, every disease, it has some genetic causes and some environmental causes. Of course, there is a lot of interaction, and for most common phenotypes, like common diseases, the impact of environment is often more significant than our genetic predisposition. However, our genome has some important qualities, some important properties that makes it very convenient for us to predict the inherited part of our of the phenotype from genomic data. So unlike environment, we do know what our genome consists of, and like, of course, there are some blind spots, but generally we do know. We can also measure it. We can, like for each individual, each individual can do a genetic test and obtain their genetic sequence that can later be analyzed. And another very important property is that our genome is permanent through our lives, and once we get the results, they stay with us, and this is why this genetic predisposition is not going to change. So how can we use it in practice? If we calculate this genetic susceptibility to a disease, like this picture, it's in the form of a polygenic score. So if we look at its distribution across different individuals, we can identify individuals with a higher susceptibility to the disease, and then we can monitor them more closely. We can assign some additional tests for them, and this is how we do not waste limited healthcare system resources on everyone, but we prioritize those who have higher genetic risk to the disease. And another important property of genetic susceptibility is that generally the dependence of phenotype from genotype is different in different populations. And this happens because of how natural selection works, and due to the fact that for many thousands of years, human populations were often isolated from each other and were evolving differently to different conditions. And this means that in general, phenotype from genotype predictive models. They're fully portable between populations, which means that if we train a model on one population and test it on another population, then the results may not be great. And this leads to disparity in healthcare because most data in like vast majority of the data in healthcare comes and in genetics in particular comes from participants of European descent. And if we apply these models trained on mostly European participants to patients from other populations, the predictions may not be great, and this may lead to poor decisions. So this is another additional challenge. So what we would want to do is to train our models that are trained on data sets from all parts of the world. And this is just a subset of genetic data sets available out there. As you can see, most of them are for people, like most of the data here are from participants of European descent, but not only. You can see here Qatar Biobank, Taiwan Biobank, and so on. So what benefits would we have by training a single large global model on all this data, or at least on a part of it? So we would, of course, we would get larger sample size, and of course, this would lead, like larger training data set would lead to more accurate models. And as already mentioned, we'll have more population diversity, which means that our models will be less biased, and also because we have larger training data set, we can include additional features such as rare variants and can investigate some additional phenotypes such as rare diseases, and we can get a lot of new insights. Right. So why do we want to use federated learning? This is mostly because healthcare data in general and genetic data in particular is extremely sensitive. And data custodians usually do not allow moving and merging the data. So we cannot just get access to all of the biobanks out there and download all of the data and train a single centralized model. Which creates an ideal scenario for using federated models. And so here we consider horizontal federated learning, and this is a cross silo setting. Right. So now we want to show the efficacy of federated models, and this is how we're going to do it. So we I need to mention that getting access to genetic data is usually not easy. You need to apply to fill the application form, then you need to wait, and so on. So it's really not easy to acquire a lot of it. So we managed to have access to the UK Biobank dataset. And what we do here is we take a single genetic data set, then we split it into nodes or clients. Then we train centralized, federated, and local models, where centralized model is trained on all of the data, all of the nodes, federated model also all of the nodes, but nodes are isolated, and local models are trained on a single node. And then we compare the performance. Of course, we expect to see that a centralized model is performing better than a federated model, but hopefully not much better. And we also, of course, expect to see that federated model is performing significantly better than a local model trained only on a part of the data. And because here we're especially interested in cross-population collaboration, we ideally would like to make our data split heterogeneous, so that we have high client dissimilarity, and this mimics the setting where we collaborate between biobanks all over the world. The problem is that with the UK Biobank, there is not much population heterogeneity, and as you can see here, the data is mostly of participants of European descent, which is why we split this UK Biobank data across data collection centers and not across ancestries. And of course, there is still some client dissimilarity because these data collection centers, they are located in different parts of the country, and of course there is still some population diversity, but not much of it. And in order to test the models in a more heterogeneous setting, we considered another data set called 1,000 genomes, which is much smaller in terms of data size, but and it doesn't contain phenotypes, but it has much higher population diversity. So it is the study was conducted to represent different populations on the planet. So this is the overview of our two experiments. So we predict phenotype from genotype on UK Biobank. And we have 19 clients of very different size, and we predict quantitative phenotypes using lasso regression model, which is basically state of the art for this kind of task, and we implement Lasso as a neural network so that we can fully benefit from federated learning. And from prediction on 1,000 genomes, we predict one of the 26 populations. Also, this data is divided into 5 superpopulations, namely Europeans, East Asians, Southern Asians, Africans, and Native Americans. Again, there is a different sample size for the nodes. So, what are our results on UK Biobank? So here on y-axis you see we plot test set R square for observed phenotype versus predicted phenotype. Like you see, like the correlation, the R square values are relatively low. This is because these complex phenotypes, they are dependent on genetics, but also there's a large impact of environmental factors. The x-axis represents different local nodes, and also there is one value for federated model and one value for centralized model. So we have 19 local nodes, and here we depict only 6 of them, not to overcrowd the graphs. And a single panel corresponds to a single phenotype. So here it's blood biochemistry phenotypes. And as you can see, blue dots, which correspond to a centralized model with centralized data preprocessing, performs best, but it does not much outperform green federated model with also federated data preprocessing. And these models much outperform local models with different ways of preprocessing the data. So you see purple and orange. And just as a matter of validation, you can see here that obviously for local models, the more data we have on the node, the better the model performs, which is how we should expect it. And there is red is baseline, which is covariates only, and this is the model that does not include genetics at all. Right. So yes, here we basically see the relative performance of federated models compared to centralized and local. So now we want to investigate the more heterogeneous setting. and we take the 1,000 genomes data and split it by superpopulation. And as you can see here, this is a very heterogeneous split. So these 5 different colors correspond to 5 different superpopulations, and you see that they are very well distinguished by the first 2 principal components, which means that like this is the majority of the variance. So what we need to do here is to tackle the phenomenon that is called client drift. I'm sure many of you are familiar with it. So if we have heterogeneous clients, because of how federated model works, or because of how federated average strategy aggregates local updates, we may not converge to where we want to. This can slow down convergence and really lead to really bad consequences. So let's see how we can tackle that. Yeah. So before that, let's see that federated model does work here. This is a train loss on one of the 5 clients, and this is a federated average with 32 epochs in a communication round. So as you can see here, you see that every 32nd epoch we have massive increase in train loss. This is after we get an update from the server. Then the loss decreases as we train the model to local data, and so on. And the important thing is that the process does converge, though slowly, and you can see that because these peaks, they decrease. So yeah, so what you see here is like the upper border of this graph is basically these peaks. Right. So now if we change the number of epochs in a communication round, we can see that things are getting better. And this is the way of how client drift works. So as we saw, federated average with 32 epochs in a communication round converges slowly, but if we communicate with the server more frequently, leaving the total number of epochs the same, we converge faster. And this is essentially how it should how it should look like. And this shows that in this setting, client drift can be successfully tackled by more frequent communication. Right. So let's see what we found and what are the limitations and the future directions of the future research. So first of all, we showed that federated learning indeed works, not only on a relatively simple task of predicting ancestry from 1,000 genomes, but also on much more clinically relevant UK biobank data. And we also noticed on 1,000 genomes that we can successfully tackle client drift by more frequent communication between clients and the central server. So one of the limitations is that this is still proof of concept, because we took a single data set, like UK biobank or 1,000 genomes, and then we split it into multiple data sets. And in a real scenario where we take multiple biobanks, there are some additional challenges. For example, the feature space can be slightly different because different biobanks may have different genetic variants that are features in our model. And then some additional solutions have to be, additional steps of data preprocessing have to be made. Yeah, so talking about preprocessing of genomic data, this is a very important step, and it is not very straightforward for genomic data. You need to remove the noise, but not the signal. And this pre-processing, of course, has to be federated, because obviously there is no point in using federated learning if you expose genetic data during pre-processing. So what else can we do? We all know that federated learning enhances privacy, but it doesn't guarantee it. So we can use some additional mechanisms. That really depends on the application. If we want to enhance privacy of single participants, then we can try using differential privacy, for example. And of course, we might want not a single global model for everyone, but we might also want to personalize this model to make it more suitable for a specific data set, while keeping all of the benefiting from the whole training data set. So these are potential future directions of the research. And finally, I want to thank people from GENXT, without whom this work could not have been possible. And there are two links. The first one is the link to our study, our paper that has just been published. And the second one is my LinkedIn. Please do add me. I'll be very happy to answer some questions now, but if you have more of them, please contact me. Thanks a lot.
Thank you so much. That was really interesting. Just as we did with the other talk, if people would like to post their questions in Slack or in the, let's see, the Zoom Q&A, or they can just raise their hand and we can take some of their questions. But while we're waiting for folks to ask something, I'll ask something. I was curious. I'm not so familiar with this type of task, and so I saw that you were predicting these superpopulations. Is that kind of the a conventional type of task that people who are exploring how you do modeling on this data often do? Is that like the MNIST or CIFAR-10 of genomics data building a model sort of thing, or maybe it's motivated by a particular need?
Right. So while it may not be as clinically important as predicting a phenotype, predicting participants, predicting clients' ancestry from their genomic data is an important product that genetic testing companies sell. So their participants give their genetic data, and the companies return some insights such as susceptibility to a disease, but also their ancestry that is inferred from genetics. And this can have it might be just only interesting for participants to observe, but also this data can to splitting participants into cohorts and then doing analysis on that.
I see. Yeah, your audio was just breaking up slightly there, but I think I could understand what you're saying there. That's cool. Interesting. I see. Again, if anyone wants to ask, happy to take them. Otherwise, I'll ask another one. I just want to double check one thing, and that was when you petitioned the data, that was based on there was some rationale for how the data was petitioned based on the location, or the institute that gave the data. So it was a natural petition.
So basically, with the UK Biobank data set, participants there were given their data at different locations in the country, and there were 19 locations, and this is how we split the data.
Based on those 19. And was it was it a fairly even spread of data? Normally, when that sort of is when that's done, there's like heavy skews one location or.
Well, of course, like in more populated areas, there were more like higher density of these centers. For example, like I don't remember. I think there were only a couple of them in Scotland, and there were like more in southern England. But yeah, I would say that it's relatively fairly reflects the distribution of population in the UK.
I see. And did you need to handle that issue in any way, or do you just train just over it, irrespective of that skew?
You mean the fact that there are different number of samples in each node?
Yeah, there's imbalanced data in the.
Oh yeah. I mean, this is a very we wanted to see different sample sizes because this is a very realistic this is a realistic scenario. So like because of how federated average weighs the data, it's this is just the strategy that we used, and it accounts for different node sizes.
I see. Cool. I guess, yeah, actually one question came in here. So they're asking how much data would you need before you could train some of these more familiar architectures? So I guess by this question, they mean, I guess transformers and, all these other sexy neural architectures that people hear about. Do you need a lot more data, or is it, or perhaps it's not even to do with the data that they asked about if you need more data, but perhaps there are kind of other things that need to be understood before you can adopt the other models, or perhaps they don't make sense for the start.
Right. So there are different models have been tried on genetic data, and of course, with like now transformers are on the rise, and I really hope to see more transformer models for this kind of data. So we were using individual genetic variants. So essentially the data was tabular, and I entirely admit that we lose a lot of information when doing this, but this is how things are usually done in this field. And there have been trained some CNNs and other more complicated architectures, and still as far as I know, the state of the art is a simple lasso regression. So there is a lot of a lot of features. So you do need some form of regularization for this. So we because we wanted to use federated model, we implemented lasso regression as a neural network.
See, makes sense.
I can see another question coming in via Q&A, and it says, are endpoints analogous to clients in FL?
No, I think that was about the last talk.
Oh, sorry. I just saw it now.
No problem. Yeah, no problem. But actually, there's one other one. I think maybe we're at the end of the time, but it's the last question. It's a very natural question, from our community. They said this seems very cool, but how would they follow along? Like, can the data sets you used? You mentioned the UK Biobank. Are there other data sets you could point them to so that they could start to build similar experiments, or perhaps this is completely regulated? They're kind of curious about doing work of this kind. It seems very cool, I guess, is what the main thing.
Right. So yeah, the problem with genetic data is that it's generally heavily regulated, and so this 1,000 genomes data set is publicly available, so you can just download the data and play with it. It does not contain phenotypic information, so it's basically just ancestry, or just these classes that you can predict. But it's still a very good starting point to get familiar with the data. And with other data sets such as UK Biobank and like other biobanks, for example, you need to apply for access, and it's often given to research groups and companies. So you need to fill in the application. It's going to be reviewed, and like you need to clearly state what you're going to do with this data, how you're going to use it. Then you need to pay a fee, and then if it's approved, you get access to the data.
Oh, I see. I see. So there is some hope to do for folks out there to at least follow a little bit in your footsteps.
Yeah,
interesting. Yeah. Oh, great. Cool. Well, we've gone past our allotted time for Q&A. So yeah, thank you very much for the talk. I'll just share the last slide here, and we can start to wrap things up. Last slide is to say thank you for everyone who joined us today. It was great to see a lot of people joining in, and we had like some pretty interesting questions around two topics that are quite different, but kind of a representative, I think, of the breadth of work that happens under federated learning, and the types of the distinct questions that we're trying to advance simultaneously to get this area moving even faster. So I want to say thank you very much to Matt and Dmitry for coming today. Great talks, great discussion. Thank you so much. And we will have another Flower Monthly next April. That will be April 3rd. April 3rd will be the first Wednesday of the month, and it'll be at 1600 UTC. But most importantly, do join us at the Flower Summit next week. We have been working with the community very hard to produce a series of features and upgrades and announcements that are going to be made throughout the 2 days. But most importantly, we're also having a lot of participation from people within the community to explain where they see federated learning going, understanding best practices for combining it with things like DP, looking at new applications. We've got, as you've seen, a lot of posters, a lot of demos, a lot of talks. So please join us in any way that you're able to do so. Hope to see many of you there, and otherwise I'll see you at the next Flower Monthly in April. Thanks very much. Take care, everyone, and thank you, Matt and Dmitry.
Thanks, everyone.